Hello AP Chemistry and welcome to Chapter 7. Again, mostly a review. We've talked about these terms last year, but now, and actually if you think about last year, Chapters 6 and 7 from this year are really all of Chapter 9 from last year. So basically we've taken the information and we're just expanding on it. And in this chapter, one of the biggest new things would be the Z-effective stuff, which is really, really important because that's sort of like the foundation for a lot of the explanations that you're going to give. So it's important that you understand that. So anyway, Coulomb's law, super duper important. We talked about that back in Chapter 4, where the basic relationship, right, is that we have a force of attraction, which is equal to, we have our constant there, right, Q1, Q2, over distance squared, right? Where, going back to defining our pieces, right, Q1 in terms of atomic properties, right? And again, we're going to use Coulomb's law all year long, we're going to see it constantly, right? Which is why it's really important. It always explains the force of attraction between charged particles, right? But we always have to make sure we stop and define what our charges are so that way we can use Coulomb's law effectively, right? Our atomic properties, Q1, we can always think of Q1 as being your number of protons. Okay, and we can always think of Q2 as being our number of electrons, right? More often, we're going to actually narrow this down to our valence electrons because most of what we're talking about, when we talk about atomic radius, when we talk about ionization energy, electron affinity, we're typically talking about what happens at the valence, right? Because going back to like the crux of all chemistry, the crux of all chemistry is, right, filling a valence, right? And so most often that's what we're talking about. So when we talk about distance, we're talking about the distance between, right, my protons and my nucleus, right? So distance between our valence and our nucleus. Okay. So then, right, make sure you have that in mind as we talk about every other thing for this chapter. Then that brings us to Z effective as our new term, right? Where what's Z effective again? Right, that's the amount of attraction to the nucleus, right, that our electrons actually feel, right? Most often discussed in terms of valence electrons. So here we have our sodium nucleus, right, with my 3s valence electron way out here, right? And we have all of these core electrons on the inside, right? Since the core electrons are closer to the nucleus, right, outermost shell is by definition, right, the outermost and furthest away, right? These core electrons screen or shield, either word is good, right? Screen or shield the valence electron, right? Meaning that they feel more of the pull of the nucleus than that valence electron, which is what Z effective gets into, right? So Z effective says the amount of attraction that that valence electron feels is based on the number of protons minus the number of core electrons, and whatever is left, right, which in this case is 1, right, is the amount of, not 1 electron, 1, right, is the amount of effective nuclear attraction that valence electron feels. Yes, does that make sense? All right, taking that and moving into some more thoughtful stuff. So, so here, right, the Z effective concept, right, is not perfect, okay? Which is why, so this is the simplest version where we have number of protons minus the number of core electrons, right? But that's not exactly true. So if you go back to your outline, right, your outline, I ask you, why is a 2p Z effective calculation more accurate than a 2s calculation, right? Because what we're not taking into account are the shapes of our orbitals, right? So going back to what we talked about previously, right, a 2s electron has higher nuclear penetration than a 2p electron, right? This says that, you know, they spend about this, about the same average time, but this one, or same average distance, this one though has that extra peak. Yes, does that make sense? Which means that the 2s electron feels a little bit higher Z effective than one would calculate just using this. Yes, does that make sense? Right. Okay. Moving along. So here, this chart is just super important because it just gives us a few things to discuss. So let's look at our chart. So here we have Z effective, right? And down here we have atomic number for periods 2 and periods 3, right? So if we go ahead and look at our lines, right, this black line is what? Right, that's just the charge of my nucleus, right? So it increases from 3 on up because this is just our total number of electrons. Right? That's what that line represents, right? If we look at this red line, what does that red line represent? Right, so that's your Z effective for your core electrons, right? We're just reading from that graph, right? Z effective for your core electrons. Now, Note that that red line tracks exactly with that black line. Why? Right, because there is no shielding for these electrons, yes? The core electrons experience, well, specifically, these are 1s, right? 1s electrons are the ones like literally adjacent to the nucleus. There is no shielding. So as the nuclear charge increases, those 1s electrons, which are still the shell closest to the nucleus, just have an increased nuclear attraction. Yes, does that make sense, right? No shielding for 1s electrons. Okay, so then that brings us to this set down here, right? This green one is that one that says Z effective is equal to Z minus S, right? And these are other approximations down there, right? And so you'll see here what we get is that we go up, 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 up across the period, right? So we could say that Z effective increases across the period. Okay, and why does that make sense? So you'll see that at the end of period 2, when we get to neon, right, we come back down here for sodium, right? And what do we notice about sodium and lithium? Right, same thing, right? And same thing again, right? So we'll note that going down a group, right? What is the trend? Right, they're essentially the same, right? Now, if you think back to your book, right, what did it say about Z effective down a group? Right, Z effective down a group, actually, right, so if we pay attention here to these more thoughtful approximations, right, Z effective down a group does increase because, going back to your book again, the larger and more diffuse electron clouds do not shield as well, right? So again, as we start thinking about larger and larger electron clouds, right, so by the time we get to shell number 3, right, we have our S and our P. We also have some D subshells like randomly spread out through there, right, which means that that electron cloud is more diffuse, right? So in terms of forming a shield, right, it's not as effective. So Z effective increases to some extent going down a group, okay? Not based on that calculation here, but in real life, right, it does increase going down a group due to the more diffuse electron cloud not shielding as well, okay? Now, implications of that mean that if nuclear charge for the valence electrons increases as we go down a group, right, that may or may not have an effect on, I don't know, some certain properties that we talked about last year, right? So tuck that away and we'll reintroduce that when we get to that section, okay? Make sense? Okay. Okay, so looking at trends for atomic radius, obviously you would have written down the trends from your book, right? Or you just remember them from last year, which is cool also. But as we go across a period, what happens? Right, radius decreases, right? Radius decreases as we go across a period. Now, if we think back, right, we already said in terms of explanations, right, we have an increasing Z effective as we go across the period. Yes, increasing Z effective as we go across the period, right? So, again, everything going back to Coulomb's law, which says that we have Q1, Q2 over D squared, right, essentially as our force of attraction, right? If my Z effective increases, we could call that one of my Q's, right? Z effective. The other Q would be my, right, this would be my valence electrons, right? Which then leaves us with my distance. Now, if we go back a couple of slides, right, we see again, like we said here, right, that on average, the distance from the nucleus for everything on a shell is approximately the same, yes? All the electrons in a shell are approximately the same distance from the nucleus, right? Obviously there are, you know, exceptions, but approximately the same distance, right? Which means that this is unchanging as we go across a period, right? So going across the period, distance does not change appreciably because we're adding electrons to the same shell, but Z effective increases, the number of valence electrons increase, which means that the force of attraction increases based on Coulomb's law. Yes, that is a great explanation, and that's what you should write every time you are asked to justify why radius decreases as we go across a period, or I guess if you want to go in the other direction. Yes, makes sense? So for the group trend, obviously as we go down a group, right, what happens to the radius? Right, radius increases. And so here, when we talk about the radius increasing, right, so if we think very thoughtfully about what we just said in the previous section, we said that Z effective increases going down a group. So can that be part of our explanation here? No, right? Because that's actually contrary, yes? So Z effective increases, but for some reason the radius still gets bigger. And what does that have to do with? Right. That goes back to this distance term, yes? The distance increases because we add shells. As we add shells and that valence is necessarily further from the nucleus, the force of attraction decreases, which means that the radius gets bigger and bigger. Yes, does that make sense? Your book goes on to talk about a couple of anomalies, right? So upon going from 2A to 3A, we'll see that in general, so from beryllium to boron, magnesium to aluminum, calcium, gallium, strontium, indium, what do you notice? Right, it does not increase, okay? And what is the explanation for that? Right, your book talks a little bit about the fact that your 2p, which is what this is, right? So this is your p, starting your p, this is the closing of your s, right? And it is true that the p subshell is higher in energy, right, than s. But in terms of writing a good explanation, the explanation for that anomaly goes back to nuclear penetration, right? And shielding, right? In that a full S subshell shields the P subshell just a little bit from the nucleus, okay? Just enough, right, that we see this little break in the trend, right? But then that trend then rights itself as we move on to the next elements. Yes, does that make sense? Okay. In addition, right, we see another break in the trend here, right? And the explanation your book gives for that is great, right? In that we have singly filled P subshells, right? And once we get to group 6A, right, that is the first paired electron, right? There is an electron-electron repulsion that is introduced there, which mitigates the increasing Z effective, right? So the increased electron-electron repulsion mitigates the increased Z effective for group 6A elements. By the time we get to 7A though, right, at that point, right, Z effective has increased enough that we no longer see that weird anomaly. Yes, that makes sense, right? In that any of these things, right, so here that full S, right, is only enough to mitigate Z effective a little bit for one addition, right? Likewise here, it mitigates for one addition. Good? All right. Ionic radii, right? Cations versus neutral. Cations are always, right, smaller than their neutral counterparts, right? We have reduced electron-electron repulsion, right? Anions are always larger for the opposite reason, right? How do we compare oxide, which is O2 minus, fluoride, which is F minus, sodium, which is Na plus, and magnesium, which is Mg2 plus? How do we compare all those ions in terms of their radii? Right, step one, we would go look at a periodic table, right? And we would see that, oh, indeed, these are what? That fancy word that you definitely need to know is isoelectronic, right? Meaning that they all have the same number of electrons. So in that case, what do we need to consider? Right, we will consider their nuclear charge, because once we have the nuclear charge, then we can think about Z effective, right? Obviously, the bigger your nucleus, the higher the Z effective for those valence electrons, which means the smaller your overall atom, your ion in this case, is going to be. Yes? All right. Next up, ionization energy. So here we are removing electrons to form cations. Note that ionization energy, the definition is relatively simple, right, in that it's always the energy required, because since we're breaking an attraction, it's always going to be a positive energy input. We'll see that ionization energy does what across a period? Right, it increases across a period, right, tracking with what we already talked about for atomic radius, right? If the radius gets smaller because Z effective got bigger, then it makes sense, right, that it's going to be harder and harder or cost more and more to remove an electron. Yes, makes sense? And likewise down a group, right? We'll see that it's easier to remove an electron as we go down a group, right? Which again tracks with the fact that the radius gets bigger and bigger, which means that that valence electron is further and further. Going back to Coulomb's law means lesser and lesser force of attraction, right? Which again, well, no, we would not use the effective there, right? But that makes sense, right? Those two things go hand in hand, right? Which is why it's really important that you understand the concept of Z effective, and then you can apply that as needed, right, to the concept of atomic radius, because then that is also your foundation for explaining ionization energy, okay? Anomalies here, right, are the same as before, wherein upon going from beryllium to boron or magnesium to aluminum, etc., right, we see a break in the trend, right, as in those electrons are not always harder to remove, right, because again, that full S subshell provides some shielding, right? And again, we get that same trend break over here, right? Again, going back to the fact that this is your first paired electron, right? Successive ionization energies, make sure you look at the chart, make sure you read the section accompanying this table very well, because this is on literally every single AP Chem exam in terms of just things that's expected that you can understand, right? If we think about ionization energy, right? So here, this is your first ionization energy. So this is the energy required to remove your first or your outermost valence electron, right? Successive ionization energies, right? So for sodium, these are the ionization energies for the first and the second, etc., right? So for argon, this is the first electron, second, third, fourth, fifth, sixth, seventh electron, right? You'll note that ionization energy always increases, right? Why does that make sense? Right, because we've decreased our electron-electron repulsion, right? Which means that now our cation's radius is smaller than it was before we made it a cation, right? And if the radius is smaller, that means the attraction between those, what valence remains, right, is stronger to the nucleus, which means that more attraction means it's harder and harder and harder to remove those successive electrons, right? What we will also notice, right, so yes, it always goes up, but there, for every atom, there is a place where the ionization energy goes up several orders of magnitude, okay? So here you'll see that this doubles, right? This goes up maybe like 3-ish, right? And then double-ish, and then it goes up several orders of magnitude, right? Like so 4, 5, or 6 times, right? Likewise here, 4, 5, or 6 times, right? Anytime we see a jump that is several orders of magnitude, that says something about that electron, right? In that electron costs more in terms of energy because it experiences a significantly stronger attraction to the nucleus, which can be explained by the fact that it is one shell closer to the nucleus, right? Which means that that's when we start to remove our core electrons. So if we did not know that this was aluminum, for example, but we saw that, we said, ooh, 600, 1800, 2800, ooh, it goes up here. That means these are valence, and this must be core, so we know that, oh, it must have 3 valence electrons, right? Therefore, that tells us something about the atom. Yes, does it make sense? Next up, we have our electron affinity trends. Here, just note that unlike the rest of them, right, you just need to know the general trend, right? Oh, and a definition, that's important, right? So this is the energy change, vague, associated with the addition of an electron, right? So you'll see that some of them are negative, meaning that addition of an electron, relatively favorable, right? Some of them are positive, right, in that the addition of an electron is relatively unfavorable, right? Which should make sense, right? We get our most negative electron affinities where the addition of one electron, right? And here, when we look at this, right, it does go back to attraction to the nucleus, right? The stronger the attraction is to your nucleus, right, the more energy will be released. And if we think about group 7A, going back to what we talked about previously, right, that's where Z effective is the highest. So the addition of that one electron, right, means it feels a relatively strong attraction to the nucleus compared to over here, right? Okay. Moving along. Oh, that's the end. All right. Thank you for listening. Be good, and I will see you soon. Bye.